David Garcia. Perez?
Perez Garcia.
Perez Garcia. Didn't put it there. About the operator spaces and the connection to Bell inequalities.
Okay, thanks, Harry. Okay, I would like to thank the organizers of this very nice, period, and in particular this workshop. And okay, I'm super happy of being here. Okay, I have two lectures to try to introduce you to operator spaces, which is a kind of mathematical theory that probably no one of you or very few of you have ever met before, and see how this is useful to understand Bell inequalities or non-local games, as Thomas was talking about in the previous lectures. So in my case, okay, the framework is more or less the same as, it's indeed the same as in Thomas' lecture. So we have a referee, we have Alice, we have Bob, and then the referee is asking questions, S and T, to Alice and Bob, and they are answering A and B. Okay. So there is some function G, depend S, T, A, and B. We depend, tells, depending on the questions and answers, whether they win or lose the game, together with the probabilities involved in the game. And then there is some values associated with the game. I would say alpha, the game, that is kind of max. Probabilities that belong to some strategies alpha, these are allowed strategies. Allowed strategies in alpha setup, because we can change the setup. Okay, of simply just sum STAB, GSTAB, probability of answering AB given ST. Okay. And then, of course, for instance, if alpha is local hidden variable, so the classical word, then S alpha, let's call this C for classical, then C would be, something like, sum of some hidden variable of some probabilities associated to the hidden variable, and then P of A S lambda, Q of B T lambda. No?
Would you mind writing a little bit bigger, please?
Yeah, yeah, of course, no problem. Yes. Sorry. So
Much bigger.
Much bigger. Okay. So should I repeat all this, or this more or less? Do you see this?
Twice
Okay.
the size.
Twice the size? Good. Perfect. So you don't see anything. Okay. So I start again.
Twice the linear size.
Okay. I think this is still okay, no? So it's kind of this side. So I have some G of STAB. This is okay? More or less? Okay. Good. And then I have some value associated with the game, which is the maximum of probabilities belonging to strategies. These are strategies allowed in alpha setup of some STAB, GSTAB, probability AB given ST. Okay? This is essentially the same setup as Thomas was talking before. And now the S alpha, so are the allowed strategies, it depends on what they are able to do. So for instance, if they can only share randomness, so they are in classical world with local hidden variables, so then the allowed probabilities are essentially convex combination of product things. If they are in the quantum case, so if they can share entanglement, they have more strategies, and therefore the value of the game will be higher. So I would write it here. So for instance, for alpha equal classical, which means kind of local hidden variable, I call it C, then C is exactly the set of convex hull, if you want, convex hull of product probabilities. No? Sorry, S, D, D. Okay, so think of the form Sorry. Okay, so this is kind of what they can do if they have no communication between themselves and they have only kind of classical resources. This is all they can do. No? Okay. So for instance, in the quantum case, so alpha. So and in this case, this is what Thomas calls simply the value of the game without any subindex. Okay. For instance, is alpha is quantum, meaning that they share entanglement, so they can share some a priori entanglement. Then SQ is exactly trace of some row shared by them, some Maris and Bob, of some POVM AS tensor FT, where these are POVMs, no? Okay? Because this is kind of the type of probability distributions they may get if they share some entangled state. It's raw. Okay? And in this case, this is what Thomas called omega star. Okay? But I can give different strategies. For instance, I can allow to some one-way communication, and this will change the set of allowed strategies and give a different value of the game. So by changing the setup, I can give different values, okay, to this type of games. And then, of course, the thing to study is how these values change when I change the setup. So, for instance, what Thomas' talk was about how this value changes by adding entanglement here, and which is the dimension of the entanglement I have to add in such a way that I play optimally or nearest optimally or something like that. Okay? Yes?
Are you assuming G is real? I mean, you've got the absolute value there.
Yes.
It could be complex.
Good question. Indeed, for me it could be complex, but because I'm interested in kind of asymptotics, so I mean, multiplying or divided by 2 doesn't matter. I mean, you can assume it is real. Usually it's real. And we may assume it's real, so there is nothing changing. Some of my games can be complex, but then either the real or the imaginary part will have the same properties. So I mean, yeah, you can assume it's real and then remove the absolute value, yes, if you want. So there is no real kind of, yes. Okay, but let me keep it, because no, it can be that the maximum is attained in the negative one, and you want this value to be positive. So even if it's real, I prefer to keep the absolute value, because I want this value to be positive. Okay. Good. So okay, so this as Thomas was saying, in the case of XOR games, in which the answers are just bits A and B, and the value of the game depends essentially only on the XOR of the outputs. I mean, not everything, but much is known. But in the general case, in which we don't have any restriction, essentially nothing is known, or okay, nothing but very few. And then the aim of this lecture is to show that there can be new, okay, when I mean new is starting in kind of around 2008. No, I mean, the mathematics came from the 80s, but I mean the connection with operator spaces came in 2008. There can be new mathematical tools which kind of may help in understanding this general scenario. This is kind of what I'm going to present here, are these mathematical tools, and then how one can use this. Okay, so okay, this as Thomas commented also, I mean, these type of games appear very natural in quantum information. First of all, they started, I mean, as Bell inequalities, and therefore in the foundations of quantum mechanics, but recently they are crucial to understand, for instance, device-independent quantum key distribution or randomness amplification. They appear also, I mean, in different kind of cryptography setup, for instance, in position-based cryptography. One can analyze also in this way. Communication complexity can also be analyzed in this way. There is a very nice review of Harry and co-authors in which they see how communication complexity can be also understood in this way. Essentially is how many bits they must communicate in such a way that they win always or almost always, and this kind of connect with communication complexity. So essentially with this setup one can understand many things within quantum information. one of the main, as again Thomas also was commented, one of the main quantities one is interested about is which is kind of the ratio between the quantum and the classical. Okay, I recover kind of, you want with my notation, quantum versus classical. So by adding entanglement to the players, I mean how much they improve the probability of winning. Okay, and because this is related to, for instance, the amount of noise the setup tolerates still being kind of purely quantum and therefore useful, or I mean to kind of the amount of randomness one can extract, or the amount of bits, secret bits one can obtain. So it's kind of, this is the quantity that at least kind of, depending on the setup, but more or less always, or philosophically always at least, one is interested in, no? To make it as big as possible. And then the kind of the aim of the two lectures, so what I maybe am able to tell you at the end of the second lecture, is a theorem due to Junge and Palazuelos, 10, I think, in which they show that with n questions, so the size of the alphabet S and T is n, also n answers, so the size of alphabets A and B is also n answers, and dimension equal n, so this is mean the dimension of the entangled state. Okay, with 1/2 there exists a game such that this quotient is up to constants bigger or equal than square root of n divided log n. Okay. Which is up to the square root and the log optimal. There is a very nice result with different tools. I think Thomas is involved and Harry also, in which they show that by putting exponentially many questions, by keeping n answers and dimension n, one can remove the square root and have n. But the price is to have exponentially many questions. In this case, it's n, n, and we have a square root. So it's not clear. But okay, up to a square root is optimal, let's say. Okay, so the aim is kind of at least to give a sketch of the proof of this result. Okay, which uses all the machinery of operator spaces, which is kind of essentially. I forgot to say that many of, essentially, okay, all the things I'm going to talk about are based on many works. The main two, characters here are Marius Junge and Carlos Palazuelos that developed many papers between 2008 and now, in which they use and develop this operator space connection with quantum information. In some of them, there are other people involved, like Thomas Cooney, who's in the audience, Michael Wolf, who's in the audience, myself, and then Miguel Navasquez, Ignacio Villanueva. And very recently also, Thomas Vidic and Oded Regev, in a slightly different context, in which the questions are quantum states, not just classical things. They also did very nice things connecting with operator spaces, and I don't know if I will have time to talk about this, maybe. So, good. Okay, so this is all the quantum information we will see today. Now we really switch to a completely mathematical lecture. Okay, so I beg you to be very patient, because you won't see any connection till the end of today or maybe the beginning of tomorrow with what I'm talking now. Okay, so it's completely switch. So maths starts. Okay? Good. I will try to be very, very, very slow in such a way that if you are interested, you can follow. Okay, with examples and everything. Okay. Okay. First of all, I will restrict to finite dimensions. Many of the operator space theory that was developed since the end of the 80s, though it can be traced back to the 60s, is purely infinite dimensional. And many of the subtleties are infinite dimensional. Okay, since we are only interested in finite dimensions, I will kill some of these subtleties just by assuming finite dimensions. Okay, but so we assume finite dimensions. I must say that even assuming finite dimensions, okay, we will not enter into that, but even within finite dimensions, some infinite dimensional things appear within operator spaces. I mean, there is no way around. But okay, I will try to avoid these things. Okay, so that's okay. Okay. So definition. So I promise, pure maths, definitions, lemmas, really maths. Okay. So an operator space X, and okay, I will say OS because it will appear many times. So just to notation is exactly CD. So vector space of dimension D with a norm. Okay, so it's a normed space. So first thing is a normed space. And this is usually called the Banach level, okay? In finite dimensions, all normal spaces are Banach spaces, so every Cauchy, so the topology is the usual topology in CD, and any Cauchy sequence converges, but this is not true in infinite dimensions. And the name comes from the infinite dimensional case, okay? Banach level, so this is normal space. But now I add to this normal space a sequence of norms. Operator space are two things, a normal space and then also a sequence of norms. N defined on Mn tensor X. Okay, these are n times n matrices, tensor X. If you want, of course, this is n times n matrices with values. Oops, sorry. With values in X. Okay. Okay, but not any norms. I mean, this sequence must satisfy two compatibility conditions. A sequence of norms there satisfying okay. Two things. One is that they behave well with direct sums. Okay, and this means simply that if I have A 0 0 B M plus M, okay. Remember that these are matrices with values in X. Okay, so I have a matrix with values in X, n times n, a matrix with values in X, m times m in the diagonal. This must be the maximum of both. So with direct sums, it behaves like the usual operator norm in the matrices, the maximum singular value, okay? It takes the maximum of both things. And it behaves well also with respect to multiplication in the matrix level, okay? In the sense that it's continuous with norm 1, okay? Behave well with multiplication on Mn. This means that if alpha belongs to Mn, so rectangular matrices from M to N, beta rectangular matrices from N to M, and X an element of Mnx, okay, then the norm of alpha tensor identity time X is right, no? Yes, beta tensor identity. Okay, this identity is in the space. Okay, this X is a very bad notation because it is the same as the space. Sorry, A. Okay, this is less or equal than the norm of this is in M, the norm of alpha, the norm of A, N, the norm of beta, where in these spaces, in M and M, we consider as always the norm is the maximum singular value, okay? We consider infinite norm, okay? Which is maximum singular value, okay? So whenever I talk about matrix spaces, the norm is always the maximum singular value, okay? The operator norm, always. This is the one that appears in alpha and beta, okay? So if I multiply at the level of the matrices, even with rectangular matrices that allow me to change dimensions, there is also a compatibility in the sense that the M norm, so see that this connects the different levels, because this M and this N may be different. So of course, all this kind of sequence of norms must be compatible within the different levels. One way of changing levels is by direct sum, but a different one also is by multiplying the matrices by rectangular matrices. There must be a continuity, okay? In the sense that the M norm is bounded by the N norms, provided that the norms of the matrices are bounded. Okay? So it's kind of a continuity statement. So this is the definition. So let me go through it again, because it's important that kind of you have this in mind. So an operator space is really many things. So it's one normness space, so a norm in CD, together with a sequence of norms in the lattices of the space tensoring with the matrices. Okay? I mean, you start to see that it looks natural in quantum information. No? It's kind of adding an ancilla of arbitrary dimension. No? With some compatibility conditions. Kind of. It behaves well with direct sums and with products at the matrix level. Essentially, this is kind of what you have to have in mind. Okay? Okay, so let me give some examples to handle these things. Okay. Example 1. X is mk. So matrix is k times k with the operator norm. I don't have to say, whenever I write mk, it's always with the operator norm. This, and then the sequence of norms comes by identifying this. No? This gives the sequence of norms. No? Where again, this is the operator norm here. So this is what we do always in quantum information. No? When we consider this as, I mean, the space of observables, for instance, and then we have another system, and then the joint observables are simply identifying this with this. No? This sort of thing. And of course, we know that these two things are verified. Okay? Because if we have a direct sum, I mean, this is what we do all the time in quantum information. No? Of course, this is continuous. If we multiply in one of the sides, we know it. And if we take direct sums, it's also I mean, it gives the maximum, no? Because you decompose the matrix is block diagonally, and of course, you get the maximum of the norms. No? So this is what we are used to, essentially, this example. Okay, so this gives, and this defines the sequence of norms. Okay? So whenever I have an element here, so I see it as a matrix, and I take the operator norm. Okay? Yes?
I'm being a bit slow. In 2,
yes.
Alpha, what is m comma n?
Rectangular matrices, m times n.
Oh, so here that would be k, use the same notation, be k comma k?
Yeah, yes, exactly. K, yes. Yeah, yes, exactly. I mean, to simplify, k is equal to mk comma k. Exactly. I mean, just not to repeat it, but yes. Okay. So this is square matrices, and whenever they are rectangular, I put both indices. Yes. So in this way, I allow alpha and beta me to switch the dimensions. Yes.
So for n equals 1, is there something that imposes the matrix norm to be the same as the...
No, this is by assumption. N equal 1 means that norm is this one. So yes, okay. Yes. The norm 1 is by definition this norm. Yes, of course, this I kind of assume it, but I should say it, of course. I mean, it's kind of the zero, we have 0 here, that norm 1 is norm 1. Of course, yes, of course, yes.
More simple question.
Yes.
So this point 2, like if we think of A as a x-valued matrix, like
Yes.
what does it look like? This multiplication that happens there, like alpha times I times A.
I mean, you use the.
I mean, what's the resulting thing, or is it, or do you get to define it how you want?
Good point. So probably the best, the best thing would be to go back to this and multiply m and see what happens. But yeah, I mean, of course you will.
Because I guess I just don't.
You will.
Like if you have.
You will probably sum the elements in X according to with the coefficients coming from the multiplication of the matrix. You use the matrix multiplication rule. There is some multiplications. The coefficients are put by alpha and beta. But then when you sum things, there is in each one of these sums there is an element of X going on. And then of course X is a vector space, so you can do this. Yes, I think this is what will happen. Yes, if one works this out. And most of the times, indeed, I mean, sometimes for simplicity it's better to think like that, but for most of the calculations, the tensor product is the best thing because you can identify what is where. No? More questions?
Is it easy to see, like, what are the possible, if x is m sub k, what are the possible norms you could have on it? Or is it?
In such a way that these things are verified, you mean?
Yeah.
Yeah, I will come to that in the second example.
Okay.
Good. Okay, so second example is, of course, any subspace of mk, I can embed it on mk and put the inherited norms. And of course, because if this is verified, and if I take a subspace, the same things are verified. So, trivial example, X, any subspace of mk with inherited norms. Okay. Good. Now, okay, if you allow me just for a second to go to infinite dimensions, and I change this mk by linear bounded operator on a Hilbert space, this example is all may happen. So there is a theorem of Ruan. Saying that x b of h, now this is infinite dimensional, are all examples.
Maybe since you've gone to infinite dimensions now, I can ask this. Is the only thing that changes in the definition that X is a Banach space?
Yes.
Okay.
Okay, so indeed, if you allow this to be the analog of the matrix in infinite dimensions, so linear bounded operators, then this is all may happen. So there is a theorem saying that. Of course, this is not restrictive at all. I mean, there are many, many things here. So indeed, every Banach space is in here. So I mean, it's really not, we are not restricting much. Indeed, for any Banach space, for any norm space, there are many operator spaces structured with associated to it. So it's a very rich thing. Okay, so it's not that this is restricting at all, but indeed, this all may happen. So you can see any operator space as concretely embedded in B of H. Okay, but you can, even if X is finite dimensional, you may not be able to embed it in a finite dimensional B of H. I mean, even for finite dimensional X, even for 3-dimensional X, you may need infinite dimensional H. Okay, this is what I mean, that even for finite dimensional cases, infinite dimensions appear. So if you want to see this concrete representation, even if X is 3-dimensional, you may need an infinite dimensional H. Okay, if you want to see this fitting into this second example. Okay, simply just a warning. Okay. Okay, so one particular nice subspace of the matrices is the set of diagonal matrices. Okay, this will be my third example. x equal to diagonal in mk. Okay? Of course, this is equal to ck, because the diagonals of k times k matrix is a c of k, which is the norm. Okay, so have x equal to sum I xi I. We know that the norm is the maximum in I of xi, no? A diagonal matrix, the operator norm is the maximum of the entries, no? Of the absolute value of the entries, no? So this is the infinite norm, no? Okay. So then the set of diagonal matrices is CD with the infinite norm, okay? Nothing magic there, okay? I take diagonal matrices, I consider the operator norm is the one I'm considering here, and I have a diagonal matrix, the maximum singular value is the maximum eigenvalue in absolute value, and is the maximum element in the diagonal, no? Okay, and notation, to simplify, because this will appear a lot, sorry. Okay. When I have CD, there will be a D here. Oh, this is a K. I'm messing everything up. Okay, so this is a K, sorry. It will be, I will put this script L, or no, not script, I mean this kind of L with L infinity to the power K, saying that this is the norm and this is the dimension. Okay. So now, this is the norm here at the matrix level, at the Banach level. Sorry, at the Banach level. No, I mean there is no tensor yet. So if I consider now A an element of mk, sorry, on Mn of L infinity k, okay, what will be A of n? So the matrix norm. So how do I compute this? Okay, because remember that to have a operator space, I need a matrix, sorry, a Banach level. Okay, in this case, is clear, is the maximum norm so of the entries, they are vectors. But I need a sequence of norms in matrix tensor the space. Okay, matrix tensor the space. Okay. Now, okay, let me put the tensor if you want, maybe it helps. Okay. So any element here is of the form. No, this is trivial, no? I take the canonical basis in C of k, okay, I denote it in the usual way, and then it must be of this form where AI belongs to Mn, no? It's always like that. So then, this is equal to, let me write it, okay? I didn't do anything. Now, see how we define the operator space extractor of a subspace. By example 2 is I take the inherited norms. So I have to put this into M of k and consider the associated norm given by example 1, that is identifying Mn tensor Mk with Mnk. So I'm going to do it. So how do I put the diagonal onto a set of matrices? Simply like that, no? Tensor, projector onto I, no? This is how I embed the diagonal into a set of matrices, no? I put it into the diagonal, no? Okay. Okay, this is what I'm doing here, is putting this like diagonal into M of k, okay? Nothing else than putting it into M of k. Now, the norm I have to consider here is the norm of Mn tensor Mk. Because by definition, the norm in my n level is the inherited norm of Mn tensor Mk. But now, the norm I consider here is the norm of identifying this with Mnk, like a big matrix. So it's the operator norm of this matrix. Okay? But then, of course, I have a direct sum structure, because for each different i's give me orthogonal things. So this sum is a direct sum. No? Because different I gives me orthogonality here. And therefore, this is equal to maximum in I of the MI Mn. Okay? Operator norm. Okay, Mn. So the norm here is the operator norm, the usual one. So once you are here, we are in quantum information means. Okay, so should I go through it again? Okay, I'll do it. I mean, just to see how all these things. So this is. So I take a subspace of MK, the diagonal ones. Okay. So, and I. Okay, so are elements of this form. Okay, so I can see, of course, elements of these forms are vectors, no? Of k dimensions. The norm is the operator norm because it's the one that comes here, and of course is the maximum of the absolute values of the elements, and therefore is the infinite norm. Okay, this is the Banach level. Okay, now I have to consider Mn tensor this space of diagonal matrices. Okay, this space L infinity of k. So I consider an element here, Mn tensor L infinity of k. Any element like that is sum of AIs coming here, tensor the canonical basis of C of k. That's trivial. So how then I define the norm? So to define the norm, I have to see this space embedded here. So I have to put the embedding. The embedding is putting things into the diagonal. So the canonical basis goes into the projector on the diagonal. No? And now the norm I have to compute is Mn tensor Mk. But then example 1 tells me that then this norm is simply the usual operator norm of this as a big matrix. But they have a direct sum structure because different i's give me orthogonal subspaces. And therefore the norm is the maximum of the norms of the AIs, operator norm. That's it. And now then I have my first kind of complete example, which is L infinity of k, that the Banach norm is the maximum, and the operator norm is, whenever I write it like that, is the maximum of the operator norms of these matrices. Okay. This is another example. Okay. More examples, for instance. So, example 4. So, for instance, the same norm space may have different operator space structures. No? For instance, example 4. Let's take x equal Cn with norm 2. Okay. So the Hilbert space of dimension n. Okay. I call this L2. Okay. Same notation. Okay, then I can embed this Hilbert space into the matrices in many ways. For instance, I can put it as the first row of the matrices, or I can put it as the first column of the matrices. And they will give me different sequence of norms, depending on how I embed this into the matrices. So the same Banach level may have different operator space structures, and it's completely different ones. So for instance, I can define Rk, it's called row space. Okay. And this is nothing but embedding, this is, if you want, embed L2 of k like that into Mk in the first row. Okay. So you want A1 AK goes to A1 AK0. Okay. I mean, it's clear that the Banach level is a Hilbert norm. Okay, it's clear that if you compute the operator norm of a sequence in the first row, is the Hilbert norm. That's clear. And now, since I embedded this into Mk, again I can go to my example 2, and this immediately gives me the sequence of norms I must put. So let me do it. So I have now A equal sum I AI tensor I belonging to Mn tensor rho K. Okay. And then, which is this norm? Okay, this norm is nothing but I apply this, have sum I AI tensor 0I Mn tensor Mk. Okay, same trick as before. I put my vector space in the matrix space, and then I compute the norm given by example 1, that is simply the operator norm of the big matrix. But now this is pretty easy to compute. If I call this B, of course this is operator norm. So if you want, this is B operator norm, the usual norm. And then of course I can compute this as B Vidaga 1/2, no? This is the same, no? The maximum singular value is exactly this, no? But now see what happens. If I apply B Vidaga, off diagonal terms cancel because I have an I with a J. This 0 is one level system, so it doesn't play any role, and this is equal to sum in I, AI daga 1/2 in Mn. Okay. Do you see it? And this defines the sequence of norms of the row operator space. Whenever I have an element in the matrix level, I can always write it like that, and the norm in the n level is given by this, where again Mn means that this is the operator norm of this matrix. So the maximum singular value, or in this case is positive, the maximum eigenvalue. I can do the same for the column. So instead of putting my Hilbert space in the first row of the matrix, I can put it in the first column of the matrix. Example 4, 5, sorry. It's column of K, which is simply L2 of K into M of K, that I goes to I0, or that is A1 AK goes to A1 AK0. No? And in this case, you have A equals sum I AI tensor I. The norm of A is the same by changing the sum I AI daga AI 1/2. Okay, it's the same by changing the daga to the other position. It's the same calculation.
Okay. I mean, just to check I'm following, this the norm on B in the top board. This is the 2 norm then of B, which is then equal to the.
Sorry.
On the top board
Here,
where you've written norm of B.
no, operator norm.
Operator norm.
Yes, MNK operator norm. MNK operator. The operator norm of a matrix is the maximum singular value. By doing B daga 1/2.
So where's the fact that it's L2 come in?
L2 is at the matrix level. So if I compute the norm at the Banach level, where I don't tensor with matrices, if I compute the norm of something like that, the norm of this object is the sum of the squares of this,
Right.
the operator norm of this object.
But this should somehow enter into the norm on the matrix level, no?
No. Remember, how do I define norms?
Okay,
I
right.
embed into MK and I take operator norms. I only take operator norms. What changes is how do I embed my space into MK. But when I embed, it's always operator norm. There is nothing. The way to embed, gives me different norm. But once I embed, the way to compute is always operator norm. Okay. So up to here, things were easy because we were able to embed always in a finite dimensional M of K. But this won't be always the case. Okay. Do you follow more or less? Roughly? Okay, good. Because things will start to complicate now. Okay. One thing I won't enter because I prefer to keep going is that these two things, though at first they may seem very similar, they are very, very different. At the Banach level, they are the same. They are the Hilbert space. But as operator spaces, they are as far as two operator spaces can be.
So David, in example 3, you embedded into II.
Yes, the embedding here, sorry, of course, the embedding, I should, probably, yes, you're right. I should say it, yes, of course. The embedded here is I goes into II, of course. Yes, sorry.
To get the same picture.
Yes, yes, exactly. Yes. So I put it into the diagram. Yes. Thanks, Javier. I think this may clarify. So, okay, these two spaces are as far as two operator spaces can be, whatever they mean. Okay. I mean, I can give you a precise meaning to that, but okay, this is kind of. So this means simply that with the same Banach level, so with the same basic level, two things at the operator space level may differ a lot. And this is of help in, to create strange games and things like that. But this will be okay. So I have now the object. So I define essentially the object, which are operator spaces. Whenever in math you have an object, you have usually morphisms associated to this object. So you have vector spaces, you have linear maps. You have groups, you have homomorphisms, and so on. No? So there should be morphisms associated to this object. Okay. So let's go to that. Morphisms. Okay, so we have a vector space with a norm, so we should have linear maps, no? Because at least the linear structure must be preserved. Okay, so have x and y, I have linear maps x and y, and I have an element here, a linear map from x to y. There is a norm, which is the operator norm of the map, which is the maximum in the unit ball of the norms of the images. Okay? This is the usual operator norm of a linear map. So this is the Banach level. And you see, essentially, that we have linearity, which preserves the linear structure, and we have some norm that tells how the norms are preserved. No? How big I can take the norm in the output if I restrict the norm of the input to be in the unit ball. No? Okay, so kind of, this is the continuity part. Now, I have different levels for x and y if they are operator spaces, so I should take this into account. No? Now, if x and y are operator spaces, here probably, and I come back to something which is familiar, which is the completely bounded norm. So it's kind of okay. So if x and y are operator spaces, I can have Tn, which is identity in n tensor T from Nn tensor x into Mn tensor y. Okay. Now I have norms in this big space and in this big space because I have operator space. And this by definition gives me norms here and here. So now I have a linear map between this big norm space and this big norm space. So I can, this has a meaning, no? The norm of this map has a meaning, no? So this is well defined. No? It's the supremum over the unit ball of this big space in the norm of the image of this big space, okay? And if I take the sup in n, this is the completely bounded norm of T. Okay? Completely bounded. And this is kind of the right notion in operator spaces. Okay, in finite dimensions there are not many subtleties because any linear map immediately has this number bounded. Okay, but the important thing is which is the exact quantity, not the fact that it's bounded or unbounded, which in infinite dimension of course is what matters. Okay, so now this gives me the space CB completely bounded from x, y, okay? That means the linear map from x, y when I consider this norm here. Okay, this is simply by definition, if you want. This, okay. Okay, later on I will make this also an operator space on itself. Okay. Let's keep things simple. Okay. I mean, everything is natural now, no? So if I have different levels, I want the same kind of continuity for all levels. I take the worst case, which is the supremum, and this defines me the completely bounded norm. Okay, the same I did for linear maps, I can do for bilinear maps, trilinear maps, and so on. So I will play Thomas' trick and keep in bilinear. Okay. So if I have now bilinear maps, now have t from x times y into c bilinear. This means that if I fix one coordinate, the map is linear in the other coordinate. Then, again, there is a notion of norm of t, which is simply the maximum, norm x less or equal than 1, norm y less or equal than 1, of the norm of t x comma y in C. No? Same as in the case of linear, but now unit ball in both spaces.
Can you take the less than equal than 1 equal to 1?
Yes, yes. In the linear case, always. In the bilinear, also, yes. It's enough to take a norming set, yes, yes. Good. So, now again, if I have, so this is the Banach level again. If I have operator spaces, now I can have T of n comma m, because in principle I can have a different matrix space here and a different matrix space here, no? And this is identity on n times identity on m times t, that goes from mn tensor x times mm tensor y into m of n m. Okay, these are square matrices, so if you want I can put also mn tensor mk sorry, tensor c. Okay. And now I see this as m of nm tensor c. Okay. I block these two first and then tensor with c. And now again I have in this big norm space, because I have an operator space, no, if x, y, and c are operator spaces. I have a norm here, I have a norm here, I have a norm there, so I can, I mean, this has a meaning, no? As before. And if I take the sup in n and m, this is the completely bounded norm of t. Same thing. Okay, I mean, soon I will exemplify this in our concrete spaces, but I need a big step more. Okay, so now the next thing is kind of probably the more subtle for today, is to see that these things, so the set of completely bounded norms, so this I will call this, okay, this gives me bilinear completely bounded, for instance, x, y, c. Okay, this will be the set of bilinear maps with this completely bounded norm. I don't know if it's the best notation, but it doesn't matter. I won't use it much. Now, the point is that both the set of completely bounded maps, okay, linear or bilinear, doesn't matter, is itself an operator space. Okay, now I'll do it for the only for the linear map. Okay, so now CB of x, y, if x, y, an operator spaces is itself an operator space. For that, I have to via the following identification. I have to identify, so I have to give a meaning, a norm, sorry, here. And then what I'm going to see is to identify this with this. It's very easy. So simply if I have an element, some AI tensor Ti, any element like that is of this form, I map it to a map T from X here that maps X to some I AI tensor Ti of X. Okay? This is the mapping. You see, if I have an element here, it's always of this form, and this T maps an element of X to an element of Mn tensor Y. Okay. And via this identification, I can make this an operator space because it's very easy to see that this object verifies the properties 1 and 2 of the operator space definition. Okay? And therefore, I have a way of defining a sequence of norms here that makes this an operator space. Okay? So, good. And why this is important? Okay, many reasons, but one is that this allows me to give an operator space structure to the dual of a space. Because the dual of a space is the set of linear maps from the space to the scalars. So if I have X with a norm, definition, okay. Sorry, X is CD with a norm. Sorry, I should say X is CD with a norm. Then the dual is CD with the dual norm, and I define the dual norm of phi as the maximum of norm of X. Okay, I should say. Okay. I would write X as a vector. Okay, less or equal than 1 of phi X. Right? Okay, the dual simply is I take the scalar product between both things, and I should write it probably. It should be better to write it as a row. There is no problem with complex numbers. Okay. Okay. An element of the dual is simply a row that I multiply by the scalar multiplication, and then I take the maximum of the unit point. And then let me finish for today computing which is the dual of our L infinity. So the example L infinity and the diagonal matrices. And this allow me, at least tomorrow I will start with the real operator space we are interested in. But okay, so then this gives, so then I can, so X, if X is an operator space, X star is also via Mn of X star is equal, X star of course are linear maps defined on X, this define linear maps on X, so this is Cv of X into Mn, okay? Because X star one can identify with Cv from X to the complex numbers. This is not completely obvious, there is a subtle step here, but okay, it doesn't matter. Okay, so then I promised the final example, which is the dual of L infinity, and this is the first example that we cannot embed in a finite dimensional M of k. So, to understand this example, we cannot see, as all the examples before, put this into M of k and compute operator norm. The example I'm going to write now, one cannot do it. So, and it's as simple as L1, so it's simply C of k with the one norm, with the operator space structure that comes from, being seeing him as the dual of L infinity. So if X now, so example, is L infinity k, so which is X star, it's clear to see that this is L1k at the Banach level, no? Is it clear that the dual of the max norm is the sum? Should I write it? Or okay, I can write it. Okay. If I have phi star, this phi is simply a sequence phi 1, phi k. This is the max of xi less or equal than 1, because no, it's the maximum in the unit ball of L infinity, but the unit ball of L infinity is all coordinates being less or equal than 1 of sum in I of phi I xi, and this is equal to the sum in I of phi I. Okay? Okay, because the best I can do if all these elements have norm less or equal than 1 is to put the norm inside by putting the phase associated to phi. Get the conjugate phase. Okay? That's the best I can do. Okay, so then, and this is the one norm of phi. Okay? Because it's the sum of the absolute values. So the dual at the Banach level, this is again Banach level. Okay? The dual of L infinity is L1. And then, so now Mn of L1 is equal to the completely bounded norms of L infinity k into Mn. So this makes L1 an operator space. With the identification I made up there, so sum I AI U1 tensor I goes to T that maps x into sum I of Ix AI. Okay? I implement the duality between L infinity and 1. So this is the map. That an element here, which is always of this form, this is the canonical basis of L1, but could be any vector, doesn't matter. I mean, I map this into a map from L infinity k to Mn simply by sandwiching x with y, and then AI is free. No? And this is an element from here. I know how to compute this norm. I define the norm here as this. And then this makes this an operator space. Because the sequence of norms defined by this identification verifies the conditions of the definition of an operator space. Okay? Okay, and this is essentially the only way to define L1 of k, because, okay, there are others involving free products and things like that, but essentially the only one can handle with finite dimensions. But I repeat, I cannot then see this operator space embedded in a finite dimensional M of k in such a way that I obtain the norm as restricting the operator norm. I have to go to infinite dimensions to do that. Okay, now, so simply, I finished simply saying that the object I'm interested in is this object, L infinity n L1 of k. Okay, and this will be the main character for tomorrow. Okay, which is mixing both one and the dual. Okay? This will be the one that appears in very inequalities. Okay, sorry, I'm out of time. Thank you.
Any questions?
This duality is in general non-reflexive.
No, sorry?
Reflexive, the dual of the duals.
I mean, we are in finite dimensions, so yes, it is. Yes. The dual of the dual, so the dual is the same operator space. Yes, one can prove it, yes.
Then let's thank David again.